Okay, so today's lesson, if you haven't done so already, you should probably locate your note packet, get it out, because we are going to take notes and it will not take very long. Yesterday we did like part one of this lesson, in which case we did things like we learned about the shape that would have been called linear, okay? And we learned about the shape that would have been called bent. And then we learned about the shape that would have been called trigonal planar. And then we learned about the shape that would have been called trigonal pyramidal. And then we learned about the shape that would have been called tetrahedral. And that is where we stopped. Okay. So now what we're going to do is we are going to learn about the last two shapes that you're going to be responsible for having some bit of understanding of. Now, the very, very first part about this particular scenario for this particular shape is that I would like to point out that the very, very first element here is phosphorus, right? And it's PF5, right? PF as in Frank, fluorine 5. Now, in this instance, so we have our phosphorus and we have our fluorines. And we have one phosphorus times its 5 valence electrons. And we have our 5 fluorines times their 7 valence electrons, which is 35. We add all of that up to get 40 valence electrons. Now, in this instance, what makes this problem or this example a little bit different than all of the ones we've done so far is there something that you have to remember about phosphorus and all of the nonmetals that come after phosphorus? What is the thing that you have to remember about phosphorus and all of the nonmetals that come after phosphorus? Yes.
Isn't it like an octet?
It's something to do with the octet. It's called the expanded octet.
Okay.
And what that means is that phosphorus and all of the elements, nonmetals that come after phosphorus have the ability, the potential to have an expanded octet, meaning that they can have more than 8 electrons around them. So with that in mind, I'm going to take my phosphorus, put it in the middle, and then I'm going to bond all of the fluorines to my phosphorus, looking something like this. And then I'm going to draw a line indicating that each of the phosphoruses have been bonded, or each of the fluorines have been bonded to the phosphorus. Now, at this point, one line equals 2 electrons, and I used 5 lines. So I used 2, 4, 6, 8, 10 electrons. So now I have 30 valence electrons left. Phosphorus is already in an expanded octet. It cannot have anything more at this point. So we now know that we're going to be placing electrons around the fluorines. Each fluorine already has 2 electrons around it as a result of the individual bond. Okay? So each fluorine needs to have 6 more electrons, right? So if each fluorine needs to have 6 more electrons and I have 30 more electrons left to go, that means that 5 or 30 divided by 5 is 6, and it looks like we're going to work out. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So now at this point, all of the fluorines have 6 dots and 2 electrons in a bond. So all of the fluorines have their 8 valence electrons. So and because phosphorus can have more than 8, in this case 10, this structure is drawn as correctly as it can be. So the number of elements bonded to the central atom in this case is going to be 5. There are no lone pairs or unshared electrons on the central atom. So we can call this in AX5 And this is what that shape would look like. Okay, so here I have a central atom, and I have 1, 2, 3, 4, 5 atoms bonded to the central atom. Okay, and so with the 1, 2, 3, 4, 5 atoms bonded to the central atom, what ends up happening is that if you can potentially imagine that from this atom to the top down to this atom appears to make like a triangular shape, and then the same thing applies here from this atom down to the bottom to the back to this atom appears to make some type of a triangular shape. So what I'm trying to get at here is there are two essential pyramids, a top pyramid and a bottom pyramid in this shape. So this shape is known as trigonal bipyramidal. Trigonal bipyramidal. So it has a central atom, and it has 1, 2, 3, 4, 5 atoms bonded to the central atom. Any questions about this? The last structure that you are going to be responsible for having some degree of understanding about is on the next slide here. It is S of 6. So I have my sulfur, I have my fluorines, I have 1 sulfur times 6 valence electrons, so that's 6. I have 6 fluorines times 7 valence electrons, so that's 42. Add them together, and I get 48 valence electrons. So sulfur is the atom directly 1 atomic number higher than phosphorus. It's in the third period. It's directly to the right of phosphorus. So sulfur also falls in the category of having an expanded octet. So I'm going to take sulfur, put it in the middle, and I'm going to draw 6 phosphorus or fluorines around it. And then I'm going to start with a single bond to each of them. And so at this point, each bond is 2 electrons. There are 1, 2, 3, 4, 5, 6 bonds. So I used 12 electrons. 48 minus 12 is 36. So now I have 6 fluorines left, and I have 36 electrons left. 36 divided by 6 is 6. Each fluorine already has 2 electrons associated with it, so each fluorine needs 6. So that looks like that works out. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, oh boy, 32, 34, 36. In this case, each fluorine has 6 dots and 1 dash or 1 line. So 6 dots plus the 2 electrons in the line make up 8. So as a result of that, every atom has 8 valence electrons, and every atom is satisfied, and a sulfur does have the expanded octet, which is allowable. The number of atoms bonded to the central atom is 6. The number of unshared pairs of electrons on the central atom is 0. So this could become in AX6. Which is a structure that looks something like this. We have our central atom. We have 1, 2, 3, 4, 5, 6 atoms bonded to the central atom. Okay. What I'd like to try to point out here is that it appears that some of the 4 of those atoms appear to be in maybe a horizontal plane, and then the 2 that go up and down also appear to be in a vertical plane. So what I'm getting at here is that this particular structure exists in a lot of different planes. but it's characterized by having one central atom and 1, 2, 3, 4, 5, 6 atoms bonded to the central atom. This structure has a special name known as octahedral. Now, the next slide you don't have, but what I'm going to try to do is take all of the different shapes and put them in one spot so you can look at that a little bit easier instead of doing all the flipping around. So some people chose to copy it like on the back side of their front cover of their notes. Some people took a picture of it, but just please bear with me because it is a good review of all the things that we talked about yesterday and today. So the first structure that we learned about yesterday was linear. And a linear structure has a central atom. It has two atoms bonded to it. And it has no electron pairs. On it, and it can be characterized as an AX2. The next structure that we learned about was bent. Again, had a singular central atom. It had two atoms bonded to it. It either had one pair of electrons or it had two pairs of electrons. So it could have been an AX2 E1 or an E2. The third structure that we learned about was Trigonal Planar. And it too had a singular central atom. It happened to have three atoms bonded to it. But it had no electron pairs. This structure could have been known as an AX3. The fourth structure we learned about yesterday was the Trigonal Pyramidal. It too had a central atom. It also had three atoms bonded to it. Oh, man. What, jeez. So it has a central atom with three atoms bonded to it. This time, this structure has one pair of electrons. On it. So this is an AX3 E1. And then yesterday we ended by talking about the tetrahedral, which definitely had a central atom. This one had 4 atoms bonded to it. With no electron pairs. And this one would be referred to potentially as an AX4. Then the 2 that we discussed today are the Trigonal Pyramidal. Which also has a central atom. It also has, but this time it has 5 atoms bonded to it. It has no electron pairs. And it could be known as an AX5. And then the last structure that we learned about today was the octahedral. Had a central atom. With 6 atoms bonded to it. No electron pairs. And it could be known as an AX6. Now, the truth of the matter is technically speaking, each of these particular structures, there is an E option available to them, even if they're not there. So I can go back in and fill in this would be like an E0, an E0, an E0, an E0, and then up here would be an E0 as well. But like the reason why I didn't do that initially, but I kind of filled it in at the end is because I'm trying to show you the pattern, right? Central atom, stuff bonded to the central atom, and the potential for electron pairs on the central atom. So that's what this chart is all about. And it's designed to help you kind of like look at things from that lens. Now, your homework for tonight is to complete worksheet 7, which is a 2-pager. It's a backside and a front side. Like when I copied it, it wasn't a front side, backside. It was a backside and a front side. So you have the rest of the hour to complete this in class. And you should be able to complete it in class. I'll mill about and answer some questions if necessary, but you have time to work on your homework. So that's that.